And hi, everyone. As Raphael said, I'm going to talk about our second generation Veyron V2, which basically has data center class both performance and features. I'm going to cover a fair amount of territory, so I'll be fairly quick. Y'all can peruse the slides offline, as well. First off, just in terms of target markets, the common thread to most all these markets is server class performance and features. Some of the markets may have some additional necessary features as well, but that is really the common thread of high performance and relatively sophisticated features. Obviously, it starts with data center. Automotive is really becoming servers, multiple servers on wheels, edge compute, AI and so on, similar, and even mobile in terms of high performance needs as well as going down from there. As we showed yesterday in Balaji and my keynote, that just a high-level view of performance, and this is socket-level performance, a spec rate score. And this is a reflection both, well, first of all, this is all normalized to a roughly common TDP of 360 watts. What this is really showing is one, high per thread performance combined with very efficient, very power efficient cores, so that within that power budget, you can have a lot of cores, and each core having a lot of single thread performance to it. And that's what adds up to that high bar compared to some of the other designs, including even like, for example, Bergamo, which kind of cuts down their performance some to be able to get the core count. Just as a quick thing in terms of at a platform level, we're full RVA23 compliant. As far as chiplets, we have shifted over to being UCIe based, as a lot of the industry is doing. As we also indicated yesterday, there's a big IPC uplift in our second generation compared to our first. I'll be talking about some of what feeds into that. There's a vector implementation. Per our keynote yesterday, we think a lot about not just CPU cores, but everything all the way out to a full platform. And that includes doing workload or domain-specific acceleration, and then we have a solution for that for our customers as well. We also provide both, what we develop both in IP form and in chiplet form. Many customers, chiplets, is very attractive, has the right economics. Some still are doing monolithic SoCs, and IP makes the most sense. First, just the high-level overview. Say in the case of a chiplet, you have what we call a cluster of up to 32 CPU cores, a 3-level cache hierarchy. First 2 levels are private to each core with 1.5 megabytes of cache within each core. In addition, you have up to 120 megabytes of cluster-level shared L3 cache. So a very beefy cache hierarchy in support of those high-performance cores. A couple of the new, bigger picture things to the cores compared to V1 is what we call macro-op caching. Others might call it op caches, decoded instruction caches. The other is a beefy vector unit, an implementation of RISC-V 1.0, plus a lot of the other more recent vector extensions on top of that. As I mentioned, in chiplet form, we've taken our link and transaction layer die-to-die controller and moved that on top of UCIe. We make that all available to our customers. And this is all a server class product in terms of full support for virtualization, enterprise class RAS. We also had the opportunity in developing this microarchitecture to do it from the ground up, building in a lot of mitigations for side channel attacks. We had sort of a luxury that many didn't have at the time when side channel attacks appeared. Okay, this is just one slide, just a quick mention of in terms of architecture support. I already mentioned RVA23 profile compliant, including many of the optional extensions. Also, a full implementation of RISC-V 1.0 plus vector crypto, the BF16 extensions, as well as some other half-precision floating point extensions, as well, and also custom matrix multiply instructions. The hypervisor extension, even in V1, we fully supported the hypervisor extension and had a full implementation of AIA. And then there's lots of other things as well. But it gives you sort of a general sense of what's in this. Starting just from the high-level summary, before I get into kind of details, that we do a lot of things rather conventionally, and we do a lot of things that are a bit different and innovative. All in the interest of not just getting high performance, but doing it in a very power-efficient way. It is, of course, a superscalar regressive out-of-order design, and going from our first to second generation, of course, like everyone else, you have more, you have bigger, you have fancier structures, et cetera. Next thing of note is in our microarchitecture, from decode onwards, everything is in terms of what we now call macro-ops, which are fused internal instructions. That was fused from a combination of 1, 2, 3, 4 RISC-V instructions. And in V1, we did a certain degree of instruction fusion. We do a greater degree now in V2 via this fusion engine that I'll touch on a little bit later. And then we cache the results of all that instruction decode in our macro-op cache. Again, sort of similar to other high-performance processor designs that have their op or decoded instruction caches. Just from an execution perspective, there are 16 execution schedulers and pipelines. That kind of lists them out. 5 integer, 3 any mix of load store, 3 scalar floating point, 5 vector computations, and I'll fill in some more details in a few slides. And a very large scheduling window in aggregate across those schedulers. So just touch on the front end first. We predict a stream of sequential runs of instructions. Each sequential run can be up to 96 bytes long from one prediction done in one cycle. It's fully pipelined, so we can predict the fetch and execution stream with pretty high bandwidth. That includes being able to handle actively predicting multiple branches per cycle. We have a large, and rather atypically, a very large first level, really a single level instruction cache in TLB, 0.5 megabyte. At the same time, though, it's fully pipelined, and we can access that with very short latency, just 2 cycles. So we kind of get pretty much the best of both worlds compared to having a large cache and its benefits, but also having a fast to access cache. And of course, there's hardware instruction prefetchers to complement all that. One other thing to note, besides just all the usual in the decode, is at the very beginning of the decode pipe, in the first stage, we decompress the instructions, we predecode instruction length, identify instruction boundaries, recognize fusion opportunities, and then that all sets up to the extraction muxes that feeds into the second pipe stage to actually go and decode sort of fused instruction combinations. Okay. Now to talk about one of the kind of more distinctly newer areas. Well, first of all, most everyone has their internal instruction set. I call it ops, micro-ops. In V2, we call them macro-ops since they represent sort of fused combinations of what were RISC-V instructions. And so our internal macro-op instruction set is sort of richer and sort of denser in compute compared to RISC-V instructions, which are very RISC-like. This, among other things, has sort of a multiplier benefit on the effective size of a lot of resources, as well as decode width, schedulers, execution bandwidth, et cetera. Since one thing in all these places really can represent multiple RISC-V instructions. Within our, if you will, main decode pipe, similar to what we had in V1, that's taking RISC-V instructions, doing a certain degree of fusion, to then produce macro-ops that get renamed, dispatched into schedulers, et cetera. And that's what will still happen for what you might call cold to lukewarm code. We'll also then recognize portions of the code that are more warm to hot, and those we'll go do some more fusion work on. And then produce that improved version of the code stream. We'll cache that in our macro-op cache. The macro-op cache is a set-associative organization, but it supports variable length entries. And in the process, we can collapse multiple non-sequential runs of instructions into one entry, which gives a number of power efficiency and performance benefits. And the size of this is comparable in hit rate to like a typical 32K byte L1 instruction cache. And given that we're mostly fetching out of that, we bypass all the typical power being burned through the instruction cache, the TLB, early decode pipe stages, et cetera. And the net effect of all this is a dynamically varying people like to talk about how wide And this dynamically varies from 5 to 15 wide in terms of both decode and dispatch. And then obviously back in the execution back end, there's up to 16 per cycle that we could execute in a moment or in a given cycle. The load store unit can do any mix of up to 3 scalar loads and or stores. Or in the case of vector instructions, we can do up to 1 64-byte vector load and 1 64-byte vector store per cycle, arbitrary alignment. We also support early load store commit to release critical resources, and then later on they get retired along with everything else. We also have a separate I and D cache hierarchies within the core so that we can really optimize the two separately for very different purposes. On the data side, we have a much closer coupling and hence a lower L1 miss, L2 hit latency compared to typical designs. Our DL1 is fairly large, 120 KB fully virtual cache, which is also kind of a notable thing that saves a lot of power and other benefits. We have your classic 4-cycle load use on it. And the key thing is this is all software transparent, meaning in hardware, we fully take care of hardware of handling synonyms, hardware coherency, TLB consistency when you're doing S-fences, and so on. Software just does its usual, and we take care of the rest. As a 1 megabyte data L2 cache, fully pipelined, 64-byte wide accesses, both writing in, reading out, filling into the L1, et cetera. And the complement to all this is an increased array of hardware data prefetchers compared to what we had in V1. Certainly a sequential, strided, multi-strided types of prefetchers, and also now temporal and spatial prefetchers as well. And of course, stuff to help manage some of those prefetchers that can tend to be a bit aggressive at times and maybe overly aggressive. The vector unit. As I mentioned before, it's a full RISC-V 1.0 implementation, plus a lot of the more recent extensions over the past year, as well as custom matrix multiply instructions. In terms of the standard RISC-V architecture parameters, it's both a VLEN and a DLEN of 512 bits, meaning 512-bit wide registers, 512-bit wide data paths. And they're all fully pipelined, and we can do multiple things per cycle. If I skip down to the lower part of the slide, there's 5 separate execution pipelines. And so every cycle we can be initiating another arithmetic operation, a mask operation, a permute operation, processing or receiving load data, and then also sending out store data. And the load and store data is not just simply, take some data, stick it into the register file, or vice versa. In RISC-V, there's a lot of relatively sophisticated munging of data between registers and memory. And that all gets taken care of by these units. With RISC-V, of course, separate register file, and so separate schedulers. It's all separate kind of little world, if you will. And we do support out-of-order execution. We do, though, instead of doing the brute force, full registry naming and everything else with buffers to be able to back out of things and so on, we actually picked a more area and power efficient design point and complexity efficient design point where we get most of the benefits of out-of-order execution, but within the constraints of not having full renaming, but again, we can still do, in practice, a lot of out-of-order execution. We also support elbow chaining. When you have elbow greater than 1 operations, they can all be interleaved based on their individual dependencies as well. And yes, moving up to the cluster level. As I mentioned earlier, we have a cluster level L3 cache, up to 128 megabytes in size when you have a 32-core cluster. That is effectively a victim cache with respect to L2s, meaning it is, I wouldn't say exclusive, it is non-inclusive. So largely you get the effect of with 32 cores, you have 48 megabytes of L2 cache in aggregate, you have another 128, a total of 176 megabytes of cache within a cluster. And of course, some relatively advanced replacement policies, et cetera. As a lot of other people have gotten into doing in recent years as well. The L3 also contains home node functionality and snoop filters that is sliced. So for example, if you have 32 cores, you have 32 slices of L3 and home nodes and so on. So your bandwidth through all that grows with your core count as well. Within a cluster, we use a coherency protocol rather similar to CHI, although better in terms of including a number of enhancements on top of it. What comes out of a cluster is standard CHI protocol. Makes it easy for our customers to integrate that into their SoCs, or if it's a chiplet form, to again hook that into their SoC fabrics. Okay, lastly, we kind of pop up to a V2 chiplet with a full 32 cores. This gives you, kind of a rough floor plan sense, not exactly to scale. And so you can see it's a two-dimensional mesh for the interconnect. And you can see the CPU cores along the left and right side, L3 slices roughly down the middle. Over on the right-hand edge are 4 die-to-die links for 32 cores. Each link is, forgetting offhand, I believe 120 gigabytes per second times 4 of them gives you enough bandwidth to keep 32 cores fed. And I mentioned that we have our die-to-die controller that supports the AMBA protocols. It also can run multiple protocols concurrently over a shared link. For us, we run CHI protocol, AXI protocol, and a virtual wire protocol over those links. And this is all now based on top of UCIe raw streaming mode. And the other thing that is appealing to a lot of our customers is that this doesn't depend on advanced packaging, interposer, that kind of stuff, which can be quite expensive. Organic packaging, does the job for most of our customers, and that's very appealing in terms of more cost-effective solutions. One other thing to mention at a chiplet level, besides the cluster itself, is that there's also a platform management and security subsystem based on a pair of RISC-V microcontrollers that are separate from the main application processors and so on. One handles your general boot and runtime, quote, what some would call platform management functions. The other handles chiplet level security functions. It plays a part in secure boot in terms of authenticating firmware that we're receiving, in terms of being able to authenticate to others that we are what we are, for example. And that is it.
So we have 3 minutes, so questions?
Mm-hmm. Yeah, as you might guess, we're not saying it publicly. Yeah. Our first generation was taped out and fabbed in TSMC 5 nanometer. And this one is, TBD was going to be 3 or 4 nanometer or 3 nanometer. So in general, a chiplet of 32 cores is not going to be that large. Oh, I'm sorry, you had a hand up first. Go ahead. I'll come to you next.
Hi, Greg. 40% is a big jump.
Yes.
So how much of that is IPC, and how much you grow core and CDIME?
So the 40% increase is on a single thread or per core basis. We are going to, an improved process node compared to 5 nanometer, and so you do get some frequency gain potentially. But at the same time, this is a larger microarchitecture, and larger tends to be a little slower. And so we'll actually take that speed benefit to enable this higher performance microarchitecture to run at the same frequency as our first generation. So the bottom line is that 40% increase is all from IPC gains. And obviously, well, I think that ties back to the earlier question of area, so. Heinrich.
Yeah, when I saw vectors, you had the specification number there. What is the state really for vector crypto? Is it really matching a ratified specification, or is it just a provisional implementation?
Gotcha, yes. Let's see. On the one hand, since I'm involved with a lot of RVI extensions, since I'm chair of the privileged architecture committee, there's all sorts of extensions always flying by all the time, and so I don't remember the exact status on the vector. I want to say, correct me if I'm wrong, that is ratified already, or it's a. Yeah, it's ratified recently.
Yeah, but that doesn't automatically mean that when you were doing your design, you had the
Oh,
ratified document, and there might be those slight differences.
Gotcha. Well, so,
like we have unfortunately seen with other chip vendors.
True, yes. Certainly, that hasn't been an issue for us since the spec has been relatively stable, over the past several months, and I think it was only one or two little, late changes we accommodated. So we're fully compliant.
This is the last one.
So what's the rationale behind you choose the CHI versus CXL?
Yeah. So on the one hand, CXL is more of an asymmetric coherency protocol. So that's one thing compared to, most people, whether in a monolithic SoC and are using, say, CHI, for example, which is a coherent protocol, or even, say, Intel and AMD going between sockets, they don't use CXL for that. They're using a symmetric coherence protocol. So that's one reason. Second is that most people live in an AMBA world of CHI, Axia, et cetera, bus protocols. And we want to be able to easily plug into that infrastructure. Our customers are getting IPs from various places, SoC interconnect, and so on. And so we conform to industry standard interfaces such as Axia and CHI.
I think that's it. Thank you very much, Greg.
Okay, thank you.